Air is being pumped into a spherical balloon. A spherical balloon. Air is being pumped into a spherical balloon. We'll put a little thing here. Okay. Determine the rate at which the radius of the balloon is increasing given the rate at which it is being pumped into the balloon. Okay. So I'm given a rate at which it's being pumped into the balloon, and I need to determine the radius at how it's changing. The governing equation for this one is not going to be Pythagoras' theorem. We have no triangles here, but it's probably going to have to do something with a spherical object. So the relationship for the volume of a sphere is 4 over 3 pi r cubed. So that is the relationship between volume and radius. You give me a radius, I'll give you a volume. And again, this is measured in meters, or meters cubed. If we take the derivative of this thing with respect to time, d by dt, we're going to get a relation, a rate of change. So it would be meters cubed per second. So let's take the derivative. So this one is going to be dv by dt equals, well, this is a quadratic. 4 over 3 is a constant. Pi is a constant. So really all my variables are. So I don't have to take derivative with respect to all these guys. Those are just numbers. This guy, I'm going to take a derivative, and it's going to be a polynomial. So 3 is going to come down, so I'm going to be left with 4 pi r squared. Now I take the derivative of the variable itself, which will be dr by dt. And this is going to have the units of meters cubed per second. Okay, it's because I took the relate. Now if I took the derivative again, d by dt again, we would have d squared v by dt squared, and we could keep on going here. It would be a little hard. It would be a product rule, because I have to take the derivative of this thing, and then times this guy, then plus this thing times the derivative of this guy. So it would be a little more complicated, but we would get meters cubed per second squared. We would get the acceleration at which this thing is happening. Okay? But we're not dealing with that right now. All we care about is, what do we want? At which the radius is increasing, given the rate at which being pumped into. We want how fast the radius is increasing. So we're going to take this equation right here, and we're going to solve for dr by dt. And that is equal to, well, it's going to be 1 over 4 pi r squared dv by dt. And there it is. That is the rate at which the radius is changing, dr by dt, as a function of dv by dt, the volumetric flow rate. This is going to be measured in meters cubed per second.